Hello and welcome to another video lesson with Koa Lawson. We're working on our next lesson in one-dimensional kinematics. We're going to start looking at vectors and understanding a little bit of how to apply them. First, we're just going to start by describing what a vector is. A description that includes a direction. Vectors are variables that include direction. The basic part of knowing the difference between a vector and a non-vector, or what we would refer to as a scalar, is really just knowing the definitions. Vectors are defined as something that have both magnitude and direction. Another way of saying that is that they have a quantity with a directional aspect, while scalar descriptors do not have direction. They're just described by a quantity and a unit. Here we see a couple of examples of vocabulary terms that describe either a vector quantity or a scalar quantity. It's not going to make a lot of sense what they are yet. You may have heard them before, and you've probably even used them in your everyday language. One of the interesting things about vectors is that they tend to be more confusing when you're first learning about them because you don't have a lot of experience or a lot of examples. While we have some definitions here we can memorize for what is a scalar and what is a vector, it's really going to be getting used to using vectors in descriptions of problems and getting more comfortable with which quantities are vector quantities because of how we represent them. Displacement, velocity, acceleration, force, and field strength are all vectors. You can't describe any one of those without including some kind of directional description. Sometimes the direction's obvious or implied, especially if we're just traveling along a straight line. However, it's important to know that even when it's implied, there is a direction there. Scalar quantities, things like distance, speed, time, mass, and energy, which have a number that's associated with them, they have a unit that's associated with them, the direction is irrelevant to the description. When we talk about a vector which has magnitude and direction has to be able to describe those two pieces of its definition. On this diagram on the right, we see a description of a vector that the vector's magnitude is described by the length of an arrow, and the direction is described by where that arrow points. A vector that represented a force of 5 newtons and describe a vector that represented a force of 10 newtons, you'd want to draw the 10 Newton force as twice as long as the 5 Newton force because it would have twice the magnitude and the length of the arrow represents that magnitude. In terms of direction, we describe that as a theta, some direction relative to either an x or a y axis, or if we're using polar coordinates, relative to what would be a positive x-axis only. How you describe any vector is going to be optional as we get comfortable with the different coordinate systems. Polar coordinates very clearly describe a vector. Polar length, or r, description of direction, or theta. If a vector has magnitude and direction, a polar coordinate, which gives you a radial length or a magnitude and gives you an angle or a direction, inherently shows those two pieces. Here we see a similar diagram. We see the arrow, which represents a certain length or magnitude, in this case r, and it's at some angle theta. What you would notice if we compared this vector with the vector on the previous slide is that it's longer. That implies that it's got a greater magnitude of whatever it's describing. The quantity or the number associated would be bigger. You can draw these to scale, and oftentimes they are drawn to scale. However, there should be effort made to try and draw them proportionally. If a vector represents a larger quantity, in general, you want to try and make it a longer vector. Effort should also be put into making sure that the direction is as accurate as possible. In this case, this is pointing in the northeast quadrant, or above the positive x-axis and to the right of the positive y-axis. If we were trying to draw a vector that represented traveling somewhere in the southeast quadrant, then we'd want to draw it differently. We'd want to sketch it differently. Again, it doesn't have to be because it's a little bit of an arbitrary decision. But as we get into more complicated descriptions, you'll find out that it benefits you if you try and make them somewhat accurate, even if not drawn perfectly. Polar coordinates are nice and straightforward. You can describe the length, or the magnitude, the polar length, and you can describe the angle, theta, and that gives you the vector directly using those two variables. We also want to be able to relate a vector to coordinate systems other than polar coordinate systems. We're going to look at how we can relate them to rectangular coordinate systems or how we can relate them to geographic coordinate systems. First, let's look at how we can relate it to a rectangular coordinate system. You take that same vector r at that same angle theta and you create a right triangle as shown in the diagram here. It allows you to describe that same segment where we treat the origin as 0, 0, and the end of the vector as some point x, y. So if you imagine there's a point here that would be x, y. When you describe this xy, xy is actually a point in space. It's actually a point in our coordinate system. It's understood that the vector would be a radial length or a distance between the origin and that point. And if you have a length from the origin to that point, it would describe this vector r. Relative to the x-axis, it would be at some angle theta. So that xy actually allows us to describe a radial length, or a vector's length, magnitude, and a vector's direction, or theta. The relationship between these two sides, x and y, this angle theta, and the hypotenuse, or the magnitude r, are the normal right triangle trig relationships, and then the Pythagorean theorem. We can describe x here, which is the adjacent side. We have our angle theta. X becomes the adjacent side. Y becomes the opposite side, and r becomes the hypotenuse. The relationship between the adjacent side, or the x, theta, and the hypotenuse is that x will end up equaling the hypotenuse, in this case r, times the cosine of theta. And if we're describing the vertical component, that's the opposite side. We wouldn't use cosine, we'd use sine. So the vertical side will end up equaling r times sine of theta. It is important to remember that this is all based on this theta. There is another angle in this triangle. It's not being shown in the diagram, but I'm going to draw it up here. If we refer to this angle, which I'm going to call phi, then we could also describe these two sides in terms of that angle instead of in terms of theta. However, y would now be your adjacent side, and x would now be your opposite side. So x equaling r cosine theta is only true when our theta is between the horizontal axis. R times sine theta equaling the vertical component is only true when the theta that we're using, or the angle that we're using, is between the hypotenuse, or the vector, and the horizontal axis. In addition to being able to describe these two sides, or how we can get our xy values for that point using sine or cosine and the magnitude and angle, we can also relate them by, once we know one side, let's say we figured out the adjacent side, x squared plus y squared is going to equal r squared, the Pythagorean theorem, a squared plus b squared equals c squared. Once we know two sides, we can determine the third. So we don't have to use trig functions for both sides. We could use it for one side and then use Pythagorean theorem for the other side. If we knew two sides, we could figure out the third, or if we knew all three sides, we don't need to know the angle. There's only one angle possible that would allow you to have a triangle once you know two or three of the sides. Once you know two sides, the third side is predetermined. Once you know all three sides, the angles are predetermined. While there are similar triangles that could have the same angle, they can't have the exact same sides. They would have proportional sides. The ratios of the sides would still be the same. However, once you have two or three actual sides, the triangle is defined, and there is only a single triangle that will meet that criteria in terms of right triangles. If we want to know theta, we could relate theta using any two sides, either using sine or cosine or tangent. So as long as we know two sides, we can determine the angles, again, based on what triangle we're looking at. The interesting thing about looking up here at phi isn't really the direction of this vector. Phi is a true angle in this right triangle, but theta is the direction of the vector. Theta is which direction I'd have to walk if I started at the origin to travel along that heading. In addition to being able to describe the position in terms of an xy coordinate, we could also describe that in terms of a geographical coordinate system. So instead of up here having an xy value, we could describe it in terms of a latitude and longitude value. And what that really means is that instead of describing the x, or the horizontal, as a positive x or a negative x value, we could describe the x as an east or west value. instead of describing the y as a positive or negative y value, we could describe it in terms of a north or south value. So again, looking at the same right triangle, if we know x and y, east ends up being relative to the x. If it was negative x, then it would be west. North ends up being relative to the y. If it's a negative y, then it would be south. And then, of course, we have to be a little bit careful remembering the previous lesson, where technically if I were to rotate that plane, so instead of traveling north along the surface, I started climbing a ladder, climbing some stairs, I could go up. So it can't be north or up. It's that if I'm traveling north, then it's north. If I'm traveling vertically or gaining a higher altitude, then it would be up. These geographical relationships again form a right triangle, so we can still apply right triangle math to this. We can still relate all three sides and the two different angles of this right triangle using our trig functions for a right triangle, because that's still true. Let's look at an example problem to try and help make sense of some of this. We have a helicopter that's flying 25 kilometers at a heading of 25 degrees north of west. Technically, if we're traveling a straight line, why don't we just call that the positive direction? But what we're trying to do is preload some of the more complicated descriptions, and in case we're not able to pick our coordinate system, but given a coordinate system where we might actually be traveling in a straight line that's not directly along one of the bearings or axes. First, we want to sketch this description, which is not really a polar coordinate, a rectangular coordinate, or a geographical coordinate system. It's kind of a combination of a polar coordinate system and a geographic coordinate system. So it's a little bit of what we call, or what I refer to as a hybrid description. First, let's sketch the vector. So relative to the west axis, or the negative x-axis, I should move towards north 25 degrees. Here we see a vector that would represent that. You'll notice this is definitely more than 25 degrees. This is probably closer to 45 degrees if we were trying to measure it. This is not drawn to scale. It'd be proportional in terms of a right triangle if we were to draw it. This forms a right triangle. Now that we have the vector sketch, we can describe it in terms of a couple of different coordinate systems. So we're going to try and describe this using three alternative descriptions to what is currently used. So currently it's 25 kilometers at 25 degrees north of west. How would we describe that in polar coordinates? Well, in polar coordinates, there's the easy part, which is the magnitude. We already know the magnitude. It's 25 kilometers. So there's our r, nice and easy. However, how do we describe theta? Some students would want to say theta is 25 degrees. For a polar coordinate system, it's based on what the positive x-axis would be as 0. This angle is not 25 degrees. What we see is that that total angle is 180 degrees. So the angle from 0 to that vector is 180 minus 25, or 155 degrees. So in polar coordinates, this vector would be 25 kilometers at 155 degrees. What if we want to describe it in terms of rectangular coordinates? Well, if we want to describe it in terms of rectangular coordinates, we have to figure out what these two sides of the right triangle would be. Again, this is my adjacent side, which is x. Since I know the hypotenuse, and I know theta, hypotenuse, or r, times cosine of theta, which if I'm going to substitute in the values, x will end up equaling 25 kilometers times the cosine of 25 degrees. Now there's two significant figures in both of those values. When you calculate that value, you get 22.6577 kilometers. But to two significant figures, that's going to be negative 23 kilometers. For the vertical part, that's going to be this opposite side. Then I'm going to use sine theta. So this is going to end up equaling r times sine of theta, 25 kilometers, times the sine of 25 degrees. When you multiply those values, you'll find out that y is going to be 10.5655 kilometers. And that's in the positive y direction. So that's going to be, to two significant figures, 11 kilometers. Another way of describing that would be to describe it in terms of geographic. Since I've already done the math, since I already know it's 23 kilometers in the negative x direction, if we were treating this origin as a northeast-southwest, that would be 23 kilometers west. And if we were treating the 11 kilometers, which is going in the positive y direction, as north, then geographically that would be described as 23 kilometers west and 11 kilometers north. And the other way we could describe this is in terms of a hybrid, kind of like we saw above here, where it's 25 kilometers at a heading of 25 degrees north of west. There's a complementary angle if we draw in the north bearing. And that's this angle here. If this angle is 25, then this angle would have to be 65. Instead of describing this as 25 degrees north of west, I could say, well, if I was facing north, I'd have to rotate 65 degrees west to travel along that heading. So this could be 25 kilometers at a heading of 65 degrees west of north.